All right, today we're going to talk about the concept of a moment and learn how to calculate what a moment is in 2D. So what is the moment of a force? It's the measure of the tendency of that force to cause a body to rotate about a specific point or axis. Mathematically, we define it as the magnitude of the force times the distance from that force to the point about which the rotation is occurring. So if we take a look at this seesaw, we have two 50-pound children. They're each 10 feet away from the fulcrum, so they are balanced. However, if we replace one of the children with a 150-pound child, and they both stay 10 feet away from the fulcrum, then the seesaw is no longer going to be balanced. We're going to have the seesaw that goes like this. So the child on the left, this 50-pound child, is causing the seesaw a rotation that is 50 pounds times 10 feet, or 500 foot-pounds, and it's tending to want to rotate this seesaw counterclockwise. In order for this to stay balanced, the 150-pound child needs to have an equal and opposite tendency to rotate. So it needs to also have a 50-pound foot-pounds, pounds-feet rotation. So in order to do that, if they were at 10 feet, that would be way too much. So we need to move them in. And in order for this to be balanced, they would need to move in about 3.3 feet. And that's the concept of the moment. It's the force times the distance tending to rotate. The one on the left is going to rotate this counterclockwise, and the child on the right is going to tend to rotate the seesaw clockwise. And in order to get them to balance, we need the two moments, the force times the distance, to be balanced. So the moment is a vector. Again, it's the force times the distance. The distance has to be the perpendicular distance from the axis about which you're taking the rotation to the line of action of the force. And the moment axis is actually going to be perpendicular to the plane that contains both the force and its moment arm. In 2D, the direction of a moment is either going to be clockwise or counterclockwise, depending on the tendency for rotation. And our convention is that if the rotation is clockwise, then the moment is negative, and any counterclockwise rotation is going to be positive. So if we have this 10 Newton force and we want to calculate the moment about that turning point, then we just take the moment is going to again be the force times the distance. So we take that 10 Newton force and multiply it by the distance from the turning point to the line of action of that force, which is 0.5 meters. So we'll get 5 Newton meters. But because this force is pulling down, it is tending to rotate this arm about the turning point in a clockwise rotation, so that moment would be negative. So it would be negative 5 Newton meters. Now it's very important again that we get the perpendicular distance from the turning point to the line of action of the force. So here we have this arm that's 4.4 meters and a force that's applied. But this distance, this is not perpendicular. So we can extend this line of action so that we can get from the pivot point to the line of action of the force the perpendicular distance, which is 4 meters. And so our moment is going to be 20 newtons times that perpendicular distance, which is 4 meters, not the 4.4. And that will be 80 Newton meters. And again, we are pulling down, so this is going to cause a clockwise rotation, and so it will be negative. And you'll notice that the units for moments are going to always be a force times a distance. So in the SI system, that's typically going to be Newton meters or maybe kilonewton meters. And in the US customary system, that'll be pounds times feet. So let's take a look at a couple of more examples. If we want to calculate the moment about O created by this 100 Newton force, we just have to take the moment is equal to the force times the distance. Our force is 100 newtons, and our perpendicular distance from O to the line of action of that force is 2 meters. So we multiply that by 2 meters and we get 200 Newton meters. The force is pushing down, so it's tending to pull this rod down, which is in a clockwise rotation, and so that will be negative. So the moment is negative 200 Newton meters. If we want to calculate the force or the moment created by this 50 Newton force about O, moment is equal to force times distance. Okay, so our force again is 50 newtons. And now our perpendicular distance from O to that line of action of my 50 Newton force is 0.75. So that is 37.5 Newton meters. And we're pushing here, so we're essentially trying to pull that thing down. So this again will cause a clockwise rotation. So this will be a negative moment. All right, trying to calculate the moment about O created by this 40-pound force. Moment is force times distance. Our force is 40 pounds. And our distance is going to be from O to this line of action. So that is going to be 4 feet plus 2 times the cosine of 30. And if you calculate that out, we'll get 229 pound-feet. And we are pulling down, so it's tending to rotate this clockwise, and so that will be a negative moment. Now, if we have multiple forces applied on a body, we can take the moment caused by each force about a point and add them together to get the total moment. So if I want the total moment about A created by these two applied forces, I can take the moment about A caused by the first one, which is the force is 3.5, and the perpendicular distance is 0.8. And that's going to push in a clockwise rotation. So this moment would be negative 2.8 kilonewton meters. And then the moment caused by the 7 kilonewton force would be 7 times the distance, which is 0.8 plus 1.2 or 2. So that will be 14. Again, it's causing a clockwise rotation, so it would be negative 14 kilonewtons per meter. So the total moment, I would just add these together, and I get negative 16.8 kilonewtons per meter. So I'm just taking the moment caused by each force and adding them together to get the total moment. Well, I can take that same problem and calculate the moment about a different point. So the forces stay the same, but the moment arm is going to change. So the moment about B, created by this 3.5 kilonewton force, will be 3.5 times the distance, which is 1.2 plus 1. And that's 2.2 times 3.5, which is 7.7 kilonewtons per meter. And in this case, it's pushing down, it's tending to be a counterclockwise rotation, so that one would be positive. And then we have the 7 kilonewton force times a distance of 1, so that's going to be 7 kilonewtons per meter times meter. And again, that is tending to be in the counterclockwise direction, so it will again be positive. If I add those together, I get 14.7 kilonewtons per meter, and positive because it's in a counterclockwise rotation. Now in this example, I have 100 Newton force applied, and I want to find the moment about O. Well, trying to find that perpendicular distance can be pretty tricky. So instead of doing that, what I'm going to do is break this force into its two components, and then take the moment about O created by each of those components and add them together. So my Y component would be 100 times 3/5, and my X component will be 100 times 4/5. And so the moment about O created by each of these, well, I'll take my y component first, is 100 times 3/5. And the line of action is here, so the distance is going to be 5. And that is going to cause a clockwise rotation. So it will be negative. And then we have the 100 times 4/5 coming here, and the distance then would be 2, and it is also going to be pushing this way, so it's also going to cause a clockwise rotation, and so that would be negative. And if I add those together, I get negative 460 Newton meters. And so that is how you would do it if you have a force applied at an angle. And now let's see if you can try some on your own.